So at low pressures, most gases obey the following four assumptions. So the gas consists of a large number of particles. 2, the particles within the gas move randomly, and their motions can be described using Newton's laws. So the laws that we've been using all semester long in terms of describing the motions of particles, they're also going to apply to describe the motions of these particles within this gas. 3, the distances between the particles is on average much greater than the size of the particles. So the space between the particles is large relative to the particles themselves. And then 4, the particles do not attract or repel each other, and their only interaction is through elastic collision. So basically we're saying that the particles don't have any interactions with either other particles or the sides of the container that they're being held within, other than through colliding with them elastically. So when a gas basically meets these assumptions, then we refer to it as an ideal gas. Now, of course, ideal gases can be described by the ideal gas law. And the ideal gas law sort of comes in two forms. The way that we sort of most often think about it is in terms of the macroscopic view. And that's PV equals nRT, where P here is our pressure, V is the volume, little n is the number of moles of the gas. So it's a measure of the amount of gas that we have. R is what's known as the universal gas constant, and then T is the temperature. And so if we're going to use this equation in SI units, we're going to use pressure in pascals, volume in cubic meters, moles is its own SI unit, temperature we're going to measure in Kelvin. And so that tells me that the value I need for the universal gas constant needs to have units of joules per mole Kelvin. And so when I calculate that out, I get the universal gas constant has a value of 8.314 joules per mole Kelvin. Now the other way that I can set up the ideal gas law is what's known as the microscopic view. So again, I've still got PV over here on the left-hand side of the equation, but now PV equals big N times kBT. So the PV, the T, they're all the same, but what I've swapped out is big N is now the number of particles, and Kb is the Boltzmann constant. So instead of looking at the number of moles, now I'm looking at the number of particles within the gas. And so that's changed what I need this constant to be. So the Boltzmann's constant, again, it's going to have units of joules per Kelvin, because I'm going to keep my pressure, volume, and temperature in units of pascals, cubic meters, and Kelvin. The number of particles is just a number, so it's unitless. So the Boltzmann's constant has units of joules per Kelvin, and I need a value of 1.38 times 10 to the minus 23rd. So sort of the two different versions here I've got the ideal gas law. One is basically having me think about my ideal gas per mole. And the other one is having me think about the ideal gas per particle. Now, these two things have to relate to each other, right? P, V, and T, they're all the same. So that tells me that there has to be a relationship between little n times R, so the number of moles times my universal gas constant, and the number of particles times the Boltzmann's constant. So I can see from my equation that those two things have to be equal to each other. And then it works out that Avogadro's number, which tells me the number of particles per mole and has a value of 6.022 times 10 to the 23rd, that's going to be what I can use to get back and forth between thinking about how these four quantities relate to each other. So one thing is that by definition, Avogadro's number lets me get back and forth between the number of moles and the number of particles. So if you take the number of particles and divide by the particles per mole, that's going to give you the number of moles. So little n is equal to big N divided by Avogadro's number. And so of course if I plug that into my equation, then what I see is that Kb, my Boltzmann constant, has got to be the universal gas constant divided by Avogadro's number. And sure enough, if you look back at the values that we had on the previous page, that's exactly the way that works out.